Hi everyone, welcome back to the FY21 CINR FOA webinar. And we are going to continue on with the NEAMS Workscopes and the MS-NE-2 Workscopes with Chris Stanek. Chris, go ahead when you're ready.
Great, thanks Julie. I'm really happy to be giving the CINR planning presentation on behalf of the Nuclear Energy Advanced Modeling and Simulation, so-called NEAMS program today. Please note that I'm filling in today for the Federal Program Manager of the NEAMS program, David Henderson. In terms of the approach to this presentation, I'll provide a little bit of context and background on the NEAMS program to hopefully set the stage for the specific NEA calls we have for FY21. So in terms of where in the NE organization does the NEAMS program reside? What's the program responsible for developing and deploying advanced modeling and simulation tools, and who manages them? The NEAMS program sits in the Office of Nuclear Energy Technologies, that's led by Sibel Shipner. And as I mentioned, David Henderson is the NE Federal Program Manager for Advanced Modeling and Simulation in the NEAMS program. And we report up through NE5, Alice Caponiti, the Deputy Assistant Secretary for Reactor Fleet and Advanced Reactor Deployment. In terms of the program itself, our mission is to develop, demonstrate, and deploy advanced mod sim tools to enable the deployment of innovations to help enable the various elements of the NE mission for existing fleet, advanced reactors, as well as fuel cycle. I should note that a challenge of our program, or something that we continuously try to manage and optimize, is balancing early stage R&D, but doing such in a way that's relevant to industry and coordinated with the NRC. We're very mindful of our stakeholders' needs and requirements, and we actively pursue research that we hope that those stakeholders will find to be relevant. We focus our efforts on several core competency areas, and I should point out that we do that in a way to fill gaps. We're trying to address gaps that exist in modeling and simulation broadly. We're not trying to reproduce existing capabilities. We really are trying to fill necessary holes that exist in that broad landscape. So our core competency areas are in areas that you might expect. Working from left to right on this slide, we perform R&D and develop code in the area of multi-scale fuel performance and structural materials degradation, as well as chemistry. And in each one of these topic areas, I list code names. I don't have time today to go through all of the codes and what they do, but the names are listed there, so there's hopefully at least a general connection with a code name in a physics area. So yeah, fuel performance, structural materials, of course, reactor physics, multi-scale thermal hydraulics, multi-physics, and then finally workflow management. As mentioned, the research that we do really does underpin NE's mission focus areas, and there are three of those: the existing fleet, advanced reactor pipeline, fuel cycle infrastructure. And I'll talk about these in a bit more detail. For existing fleet issues, are very interested in addressing core performance issues that increase operational costs, with the long-term vision to ensure availability and market competitiveness of nuclear energy through our existing fleet. Moving on to advanced reactors, we really see an opportunity for our program to accelerate the development and commercialization of non-LWR concepts. Hopefully we can use ModSim to help interpolate between very valuable experimental data points. And we work very hard to support our partners in the NRC in their mission to perform confirmatory analyses and ultimately license these reactors. And then over in fuel cycle, there's work that in principle can be done around the area of used nuclear fuel, performing high fidelity analysis and of that used fuel with the tools that we're developing for fuel performance needs. Let me drill down a little bit further into what we're doing in the existing fleet. So as I mentioned, the idea here is to provide computational capabilities to our stakeholders, vendors and utilities, to address important fuel and core issues. And so here we're thinking about things such as corrosion, fuel damage, and such. And a particular point of interest at the moment is our advanced fuels, both accident tolerant fuels and also thinking more about extended burnup. And so we're very interested in accelerating the development and approval of accident tolerant fuels. We're interested in load follow as more as the energy portfolio becomes more complex and the nuclear power plants are being asked to operate in different ways than they have in the past. But with an eye toward the future, we're very interested in taking these fuel performance tools in particular and extending them to high burnup fuel. For advanced reactors, we really see a very pronounced opportunity where we can assist in the acceleration of design and employment of non-light water reactors. Using our tools, for example, in the design optimization process, or for example, using our tools by the NRC to expand upon their existing capabilities in order to perform confirmatory analysis. Again, I mentioned data availability. You know, that we see a strong need for advanced ModSim in regimes that are data poor, so to say. And so if there are opportunities where either ModSim can help direct these difficult experiments or potentially even reduce the numbers of them, that's something that we're keenly interested in. I should point out here, though, that one of the comments I often hear when talking about advanced ModSim is that we have interest in "quote unquote" replacing experiment, and I want to dispel that myth very explicitly. And nothing could be further from the truth. Our interest in our program is to provide tools into the toolbox that work in conjunction with experiments to solve hard problems that are of relevance to the industry and the NRC. There's already some use of our tools by the advanced reactor industry. I'll mention some work we're doing in collaboration with the NRC. But we see this as a very exciting area for successful commercialization of some of these concepts. So just a few words on our collaboration with the NRC, and the way this has evolved. Our collaboration with the NRC most certainly is helping drive the priorities of our program. And so the so-called comprehensive reactor analysis bundle, this image is courtesy of the NRC. That acronym is CRAB. So this is the the mod sim approach that the NRC has indicated that they will use for the analysis that they'll perform on non-LWRs. And what's of interest to the NEAMS program is that these code names in light blue, some of which I've already mentioned in an earlier slide, these are codes that are developed by our program. And given that importance, of the use of this particular use case by the NRC of these codes, this really makes these codes very high priority for our program. That said, that's not all of the codes that we develop, and here we're just trying to provide a bit of a legend or a reference table on the codes that we work on, or either lead the development or contribute to the development of, for a range of different physics areas for both light water and non-light water reactor. And again, in the interest of time, I won't go through all of them now, but hopefully this table is useful to you. Before talking in a bit more detail about the specific NEAP calls, I want to spend a few moments just discussing what we're doing in the area of chemistry. This is particularly important. We do have a few calls in this area, given its importance to the advanced reactor industry. So what we've heard from our molten salt reactor stakeholders in terms of what their mod sim needs are has really led to us instigating some efforts in the area of molten salt chemistry. And I should point out that the work we're doing here is coordinated with the Advanced Reactor Technologies MSR campaign, as well as related efforts in NE4. So I think it's probably easiest, and again, in the interest of time, there's three main categories of work that we're doing in the area of salt right now. The first one here, this main box, this large box, is in thermodynamics. It's a particular emphasis of our program to contribute to the development of the so-called molten salt thermodynamic database, otherwise known as MS-NE-2. This is just a list of some of the compositions that are included in that database. This database was also the topic of an FY20 NEAP award that will expand investment into this through work at the University of South Carolina. Moving over to the right-hand side of this slide, physical properties, thermophysical properties, density, thermal conductivity, heat capacity. Being able to calculate some of these things, again, to interpolate between very sparse and valuable data points is the goal here, using ab initio techniques. And some of our early results here, we think, are very encouraging in terms of demonstrating the approach we're taking to some of the more complicated salt compositions. And then finally, systems analysis. Our main tool for systems analysis is so-called SAM code. We are investing in the extension of SAM to MSR and FHR capabilities, and I'll talk more about that as I go. So that brings me to the first one of our NEAP calls, NEAMS 1, Advancing Material Modeling in SAM. I should point out that Ray Hu at Argonne, the lead SAM developer, is the technical point of contact for this call. What we're very interested in this particular call is to support the development within the SAM code of materials transport modeling capabilities within SAM. And so here we're thinking about the transport of corrosion species, contaminants, as well as fission products. It's very important that the work done here is coordinated with SAM development efforts, must be computationally efficient to not interfere with the running of the SAM code. And we're very interested in approaches such as reduced order models into the SAM code for this purpose. Moving on to NEAMS-2, I mentioned that we are performing work within the program in both structural materials and chemistry. We're really trying to work up to the point of developing a rigorous corrosion capability. And so in NEAMS-2, we're very interested in creative solutions to corrosion modeling for molten salt facing structural components. Of course, there are several non-light water reactor designs that fall into this category. And so the corrosive nature of the salts introduces some challenges in terms of the performance of a structural material. And so we're very interested in sort of a structural materials health monitoring context of developing robust mod sim capabilities that can predict the evolution of corrosion of such components, ultimately at an engineering scale. And so in terms of scope, we're interested in capabilities that simulate the processes involved in corrosion in alloys relevant to these MSR reactors. And when I say MSR, I should note that I'm also referring to FHRs. We note that physically realistic models will require simulating behavior that occurs at the mesoscale, so-called, at the material microstructure. And so it's an expectation of this particular call is that there's line of sight between what might be done to simulate corrosion at the microstructural scale, but have that eventually inform our finite element base code, so-called Grizzly code. There's also work that we're doing in this area for high temperature mechanical properties. And the expectation here is that the proposals will rely on existing NEAMS capabilities on this particular topic. I should point out that Ben Spencer at Idaho is the technical point of contact for this work. Okay, moving on to NEAMS-3. Here we're interested in, so we're shifting gears a little bit from chemistry and corrosion and molten salts to gas reactors. So here we're very interested in next generation high fidelity pebble bed simulations. So in terms of background, a major challenge to current gas reactor analysis or pebble bed reactor analysis is the creation of accurate multi-group cross sections during depletion. And so the point here is that the spectrum of pebble of a certain burnup sees in the core depends on where in the core it is and the composition of the pebbles around it. And so this is a computationally challenging problem. So currently there are approaches that rely on homogenizing regions in the core, not individually tracking pebbles. And so the NEAMS program is developing capabilities to track individual pebbles, but that yet hasn't been extended to pebble depletion. And so we're very interested in proposals that address these issues. We acknowledge this is a bit of a scientific grand challenge, but we're really interested in the creativity that exists in the university or university collaborators to help us sort of, move beyond what we're doing now in this important area, and really improve the accuracy and fidelity of pebble bed reactor depletion simulations. Here we're thinking about not only the equilibrium core, but also the so-called the running in phase, the transient phase before reaching that equilibrium core. And we fully expect that new methods will have to be developed for this. And it's computational expense is expected to be rather high. And so that's just something that we want to put out there that we acknowledge. But this should set the stage for example, for reference calculations with these methodologies, which can be used to benchmark some of the lower fidelity simulations. Nevertheless, the capabilities that are developed as part of this particular call are fully expected must be integrated into the NEAMS reactor physics tool called Griffin. Okay, moving on to NEAMS 4, another grand challenge is two-phase flow. And so here we're looking at fundamentals of multi-phase boiling flow for high pressure, high void conditions. And so background here is that the prediction of two-phase flow is essential to the operation and performance of LWRs, as well as the secondary side of many non-LWRs. And so we're very interested in improving our ability to simulate boiling two-phase flow. And key parameters of interest are void and pressure distribution over the range of boiling regimes that go all the way from bubbly to annular flow. Very interested ultimately in connecting to dry out for the reason that contributes to fuel failure. So the fundamental understanding of two-phase flow, and here we include measurement of high pedigree data is essential to advancing our predictive abilities. So here, in terms of scope, we're looking for proposals that are able to characterize flow boiling characteristics in high pressure, high void fraction regimes. This is high-res multi-phase thermal hydraulics and development of closure models for boiling, and interested in connection or inclusion of those closure models in the tools that we use for this purpose. The two-phase variant of NEC 5000 referred to as NEC 2P for CFD, and then CTF in terms of subchannel. Okay, moving on to our last one, NEAMS 5. And again, keeping with our theme of scientific grand challenges, we're interested in time-dependent Monte Carlo simulation capabilities. Matt Jesse is our technical point of contact on this particular topic. As is well known, continuous energy Monte Carlo is generally limited to steady state configurations and operations. And so what's prevented transient Monte Carlo are essentially just the particle histories required. The number of tallies make this computationally difficult. So what we're interested in here is method development for a computationally efficient, time-dependent Monte Carlo capability. Really, again, we expect very considerable computational expense here, and so interested in this capability for reference solutions for our lower fidelity reactor physics codes, Griffin and Vera. Here we're interested in proposals that focus on methods and algorithms and pursue novel approaches for error control, hybrid approaches for sampling and acceleration for multi-physics iterations. And as with the other proposals, we're very interested here in proposals that knowledgeably connect to the Monte Carlo code where we do our development, which is in Shift. then finally, let me say a couple words before opening it up to questions for nuclear data. I don't think I need to belabor the importance of nuclear data for simulations of nuclear reactors, and there's some context here about the importance of all that, but I assume that that's very well known. So let me just jump right into the description of the work scope we have in this area. And so we're interested in improvements that address nuclear data needs that are very clearly demonstrated to be a limiting factor in nuclear fuel and reactor design, analysis, safety, and licensing. So we're looking for proposals that improve improve nuclear data. That can be in the form of new nuclear data measurements, evaluation of nuclear data in the appropriate formats such as NDEF, inclusion of variances, processing into usable forms, and so on. I want to draw your attention to the bold statement here at the end of this slide, which is that a key element of this work is to focus on to make sure that there's a connection between the work proposed and the deployment or operation of a reactor. And it's mentioned in there very explicitly that a letter of support or some description of how this work will have an impact on industry is it would be an example of articulating that importance. And with that, I apologize for not leaving too much time for questions, but I believe there are a few minutes for questions.
Okay, would you like me to unmute the TPOCs before we start?
Yes, that's a good idea.
Okay, I'll unmute Ben Spencer, and let's see, Matt, Jesse. Okay, and Ray Hu. Here we go. Okay, I think all three people are unmuted now. So we have a few questions here. Let's see, first one. In NEAMS 1, what specific fission products are desired? Since tritium is already heavily supported by NEUP and DOE programmatic funding. Excuse me.
Yeah, that's a good question. Ray, I don't know if you want to take that, but you know, from my point of view, I think the obvious ones such as cesium and strontium would be of interest. We also mentioned corrosion products there, and so we did leave that a bit open to interpretation. But I think it's also yeah, I would say we're not looking for something necessarily exotic. It's what you'd expect. And Ray, I don't know if you have anything to add to that.
Sure. Yeah. This is Ray. So I think the specific trillion. That's something we will not stick in this NEUP call. The primary reason is there's a near-term needs in an industry collaboration project. So I think the timeline for NEUP may not match with the near-term needs. So I think the same development team will need to work on trillion transport directly with other collaborators. So I think, but this call is more general. I think including fission products, cesium, and certain corrosion products as well. It's relatively general, but particularly on trillion transport model, we're not speaking trillion transport model in this call.
Okay, next question. What reactor designs fall under the preview of NEAMS 1? Any and all non-LWRs?
In principle, yes, but I think the particular interest in salt is of particular interest. And Ray, please feel free to add to that comment.
Yes, in general, it's open to all reactor types, but in terms of near-term needs, the salt-cooled reactor is certainly something we want to attack in the near term.
Okay, in NEAMS-2, would a combined experimental computational focus be of interest?
Potentially. I think that's a hard question to answer without knowing what specific experiments, but they weren't explicitly prohibited in the call, and so I think it would be on a case-by-case basis. Ben, I'd look to you maybe for some clarification on that.
Yeah, I think I would agree with you. Yeah, I was going to look to you for clarification. Yeah, I don't think it's completely out of the realm of possibility, but in general, the main emphasis should be on computational work.
That's a real important point. Although it doesn't prohibit experiments, I think an exclusively experimental proposal would not be responsive to the call. I think we really are interested in the development of corrosion models that would ultimately reside in the Grizzly code. And so, you know, experiments for validation or to help resolve some important physics and chemistry in this case, I think would be worthwhile, but it shouldn't dominate the effort, I would think.
Yeah.
Okay, for NEAMS-2, would proposals involving model development and new experiments for validation be of interest? I think you might have covered that.
I think we just answered that one, yep.
Okay, sorry about that.
Nope, no, it's a good question.
Okay, should in NEAMS-2, should projects use the NEAMS tools such as Yellow Jacket and Grizzly?
Yes, it's acknowledged that there might be some other things that would be part of a proposal, but those should be the final product, let's say, should find its way into the NEAMS tools.
Okay, again, NEAMS-2. Are there enough corrosion experimental data for calibration and validation of mesoscale models, or are we allowed to propose performing experiments too?
It's a popular topic. I think we've answered that one.
Okay. NEAMS-4 scope. Could you please elaborate on how high the system pressure is expected to be in experiments?
Ray, I'll give that one to you.
I think as long as it shows the pressure effect importantly, I think that's acceptable. We don't need to go all the way to the, you know, to boiling water reactor operating conditions, 7 megapascal. But I think as long as it demonstrates the importance of pressure effects, I think it's acceptable.
Okay. On the SAM code, is it only for one-phase flow or is two-phase flow desirable too?
So the code right now is focused on single-phase flow modeling. I think for species transport, we basically assume the species transport together with the fluid, so basically still single phase. This is certainly a very large assumption. If proposals seeking different approaches, we're open for ideas how to develop models, but still within the current code structure or current single phase flow framework.
Okay, is there any interest in two fluid model fundamentals related to NEAMS 4?
So we're not seeking on two fluid model development in this call. So we're seeking high fidelity, high resolution experimental data, closure model development suitable for the tools we're developing within the program. So this is NEAMS-2 for CFD and the CTF for subchannel closure models.
Okay, for NEAMS 2, do you have any particular type of alloys in mind, say nickel-based alloys? And do you think integration of machine learning tools with existing microstructure-based codes will be within the scope?
Ben, do you want to take that?
Yeah, sure. So I would say any of the alloys that are allowed by the boil and pressure vessel code for high temperature applications would be of interest there. This is something that's a pretty new area for us that we don't have. I think the options are pretty wide open there as long as they're viable candidate materials. And then the other question about machine learning, yes, that would definitely be of interest.
Just to add to Ben's comment and just put a very fine point on it, I don't think that we intentionally didn't specify alloys, but we're particularly interested in alloys that are being pursued by our industrial stakeholders. And in terms of nickel alloys, I would just make sure to connect the alloys of choice to industry, potential industry usage.
Okay. For NEAMS 4, is the focus on experiments or modeling? Any suggestion on measurement techniques?
So I think it has elements of both experiments and the modeling. I think the proposals can focus one or focus on both sides. I think both are acceptable to us.
Yeah, and in terms of experimental techniques, we've left that intentionally vague. We're interested in what sort of solutions might be out there.
Okay, for NEAMS 2, do you want to model specific molten salt reactor structural alloys?
I think we covered that in 2 questions ago.
Sorry.
No, it's fine. These are good questions.
Okay, for NEAMS 3, is neutronics method desired to be deterministic only, or the Monte Carlo method is okay too?
That's a good question. We didn't specify. Ultimately, we would, we wanted introduced the method into the deterministic Griffin tool. If there are Monte Carlo solutions there, I don't think that we would that would be of interest as well. But that I also point out that we're interested in the transient phase, and so if a proposal is able to do that, it would essentially be doing NEAMS 3 and NEAMS 5 at the same time.
Okay, does studying salt chemistry data and property prediction fall under any of these calls?
Not explicitly. The closest one would be NEAMS 2 for corrosion. But here we're more interested in the corrosion mechanistics and a model, developing models for corrosion that requires some understanding of salt, but isn't an explicit generation of salt thermochemistry or thermophysical data.
Okay, in NEAMS 2, would fundamental understanding of the corrosion electrochemistry be included?
Absolutely, yes.
Looks like this might be our last question. In NEAMS 4, can you please confirm which flow regime is the priority?
So I think the high void fraction region is the priority.
Okay. I don't have any other questions. Do you have any other comments, Chris, or any of the team here?
I don't. I appreciate everyone's attendance and the really good questions, and look forward to a good set of proposals.
Now I just got 2 more questions in. If NEAMS 2 is focused on modeling capability, do you think a model alloy would be of interest?
It depends what's meant by model alloy. If the question is if the proposal would be based around a particular model alloy, say a certain stainless steel, yes, I think that would be.
I think you just cut out, Chris. Are you still there, Chris?
That's strange. Can you not hear me?
Now I can hear you. It cut out for a minute. That's just kind of weird.
Odd. Were you able to hear the answer to my question?
Please, why don't you state it again, please?
Okay, sorry about that. Yeah, so not sure what's meant by model alloy, but if, for example, a specific well-known stainless steel alloy was selected to be the basis for the corrosion work, yes, I think that would be a good approach for this particular call.
Okay. And then are any flow conditions of interest in NEAMS 2?
Yeah, we haven't thought, well, I would say that this is more of a chemistry problem than a thermal hydraulics problem. And so we haven't specified flow. Again, I guess the answer to that would be anything that's relevant to the MSR and FHR designs that are being pursued.
Okay. And I think you answered this one, but I'm just going to ask it again just in case. NEAMS 2 are conducting corrosion experiments. Would they fill the scope of NEAMS 2?
Yeah, again, I think we're open to experiments, but the proposals should not be exclusively experimental.
Okay. And then here's one more. Are you interested in stress effects on corrosion in NEAMS 2?
Yes, potentially. If I think that's not, I think our thought here was that there was enough difficult problems just around the corrosion with salt, but the stress effects, if they were to be included, I think, yeah, that's that would be viewed positively.
Yeah, I would add there, that's one of the things that was specifically called out of interest, actually.
Okay, great. For NEAMS 1, what type of molten salt reactors are more interesting? Solid fuel or liquid fuel reactors?
I don't think we don't specify.
I'm open for both.
Okay, I think that's all we have for today. Thank you very much, everyone, for participating, and to our speakers. We do have another Workscope at 5:00 p.m. Eastern time today, and it's for RC11. We'll see you all back then. Thank you. Bye.
Thanks, Julie. Bye.